All right. So digital signatures are a critical piece of Bitcoin. And think of cyberspace and everything in cyberspace and online. It is nothing more than zeros and ones. And this here is all that's out there, zeros and ones. And you've probably heard these sayings before: Bitcoin is a digital asset, or Bitcoin solves the copy and paste problem. And these are true statements. So I went and pulled a recent transaction off the blockchain. You can view all the transactions and block happenings at this address. And in this particular case, there's about zero point zero 0.03 Bitcoin being transacted. And from the same website, I could pull the code. This is the actual zeros and ones of that transaction, and I just copied it right off the website. And this zero point zero 0.03 was sent from this address to this address. But all of this data is publicly available to anybody, and it's also just zeros and ones. So how can this person claim this? How can this person here claim this Bitcoin as an asset? Why can this information not be copied and pasted? And a large part of the answer is digital signatures. And the elliptical curve digital signature in Bitcoin is very similar to the digital signature algorithm. But we're going to start with the first one that was invented, which was the RSA digital signature. And recall from RSA public key that we had a public key and a corresponding private key. So Alice would encrypt her message using Bob's public key, and Bob could decrypt it. Bob is the only one that could decrypt it using his private key. And the signature scheme works mostly the same. So Alice has a message, going to send it to Bob. But first, we'll pause a second. We need to talk about this problem, and the problem we need to solve with the signature. Why we have signatures, and it's not necessarily that intuitive. So imagine for a second this document, and Alice is promising to pay Bob the money that she owes him. And this is a document that Bob is going to want to hold on to. It's an important document, and it's equally important that he is 100% sure that it came from Alice and not some imposter. And Bob gets this document from Alice, so he has it. But worst case scenario is Alice is not going to pay on time, and Bob will now need to take this document to court, and he has to prove in court that Alice was the only one who could have signed this. And Alice can't say, oh, it wasn't me, or just something along those lines. And this seems like a kind of obscure problem, uh, but the situation is actually all around us, where we just have to have this solid proof that could go in front of a judge, and it would be unequivocal, without a doubt, that this document came from this one person. And this kind of protocol to ensure this is going on behind the scenes all the time in our browsers and our smartphones. It's always taking place. And the problem has to do just between these two individuals. It's to protect them from each other. So we're no longer talking about some third-party eavesdropper, or someone who's got nefarious intentions trying to steal your message. We're talking about just the need between these two people to prove that a message came from one person to another. And the RSA was the first published solution for this. And there's another half of the problem that we're going to have to get to in a minute. So hold that thought right now. The problem is just between these two people. So, and here's what the process looks like. Alice is going to take her message, she's going to put it through some hash function, and what she gets out, we're going to call it M. And just for this example, we'll use ripened. M will be 160 bits, but we could also use another type of hash, any hash, maybe 256 bits. The idea is that M is always going to be a predictable amount. And Alice has her public key N and E, and she has her private key D. And now this is the easy part. Alice's signature, this is her signature. This is her message raised to the power of her secret key modulus N. And the plain text message plus her public key and the signature are all sent to Bob. And Bob can now use the public components to verify the signature. So now back to the problem. Notice that in this example we just went through, the plain text is going straight to Bob, so anyone could intercept it. Well, actually, to get past this, you have to use some kind of shared public key protocol, and you have to establish a shared secret key, and you're going to use something like DES. And now Alice is going through her signature process and sends this information through something like DES, and it makes its way to Bob. And this is the important distinction. This is the second half of the problem of why we have signatures. So in the public key protocol, it's protecting the document from a third party or some kind of bad guy looking at it. The public key protocol is keeping this plain text message a secret. But it requires both individuals access to the same key. They share the same key. Now, when we're talking signatures, this is an extra step. It's an extra key, and only Alice is going to have this key. So with a shared key only, Bob could just make up a document, a fake document, says Alice is going to pay him, and it's signed with a secret key, but it's one that they share. So there's no way to be sure if Bob made it up or it genuinely came from Alice. And that's what this extra step solves. In a signature, only the person with this one secret key can make the signature. And this is proof to everyone publicly in the world, that this signature only came from the person holding this key. So then now we'll walk through the steps now, clean the slide up. So Alice will determine a public and a private key. She's going to get the plain text message plus the public key to Bob, and she also signs, we'll call her signature S, and this goes to Bob as well. So now Bob has the new public key, and this is not the one from DES, or this is not the shared key. This is the one that's related to the signature. And Alice is the only one who has the secret that's tied to the signature. So he's going to use the same hash function. He gets M, and he has S. So Bob raises S to the power of E, this is Alice's public key, and then he checks that the answer equals M. And if this is true, then this tells him that Alice is the only person that could have signed this, and it's a valid signature. And if it's not true, it's not a valid signature. So we'll walk through an example. Alice has her public and private key. She has her message. She's going to go through the equation here. The remainder is 16, so her signature is 16. All of this gets passed to Bob. Bob takes the signature, raises it to her public key, and as a result, the remainder is going to be 4, which is the message. So he has verified that this equation here equals the message. So this is a valid signature, and it came from Alice. So for the RSA, in conclusion, it's the easiest protocol to kind of wrap your head around. But we do need to cover the ElGamal. It's similar. It has a couple extra steps, but the ElGamal is the foundation for what Bitcoin uses. And the ElGamal was an evolution over the RSA protocol. So the RSA protocol was running into issues having the message and the signature traveling as two different pieces. So I mean, it would work, but you could have situations with a valid signature even if the message was tampered. And again, you would still be able to catch this in the protocol, but it was a nuisance, and there was a need to bundle these together just to get rid of that potential headache. So this is where the ElGamal came in. This is a bundling of the message and the signature. And the RSA was based on the integer factorization problem, whereas the ElGamal was based on the discrete log problem. So Alice is going to use a circle of numbers up to p-1. She's going to have a generator, her secret A, and then her public value X. And then she has the plain text message and the hash of that message M. And now here's the only additional step, and that's Alice uses 2 public and private keys. So K1 and P1 need to be a multiplicative inverse, and this is due to the encryption and decryption procedures. And in addition to being a random secret number, K is also co-prime to P-1. The protocol requires that. So this is going to ensure that we get the inverse of K. And the inverse, this is the symbol for an inverse. This is not like K raised to the -1. This is the symbol for multiplicative inverse. So we've seen this a few times now for how to calculate this. We need the extended Euclidean algorithm, and the number that we find here that makes this equation true will be our inverse, and we'll see that in the example we're about to do. So back over to Alice's side. Here is the bundle. So this is the signature. It's a function of both private keys. Here's K, or the inverse of K. Here's the secret A. And it's this extra step and then some math is what now allows our message and our signature to be bundled together. So Alice sends all of this, and you know, Bob gets her public key information. This is the generator, as well as her public key number 2 info and the signature. So you know, Bob's going to compute these two equations, and he checks to see if they're equal to each other. So without going into the details, the proof behind this is you can get down to these two expressions and compare them. So with these two expressions, we can subtract AR from both sides, and then we take the inverse of K on both sides, and we end right back up with the signature equation. What this is telling us is, as long as the signature with the bundled message was done correctly, that is how you verify that the signature indeed came from Alice. So a quick example is our public key number 1 and our public key number 2 with the special consideration when we selected our K, so we know an inverse of K mod P minus 1 exists. And now Bob has all of this information. And when he verifies, he's going to find that they do match and we have a valid signature. And the last point is, you know, Bob only needs the public information to verify the signature. Both of Alice's private keys stay protected. And this is due to the intractability of the discrete log problem. Her private keys stay safe. So for our next topic, the digital signature algorithm, which is very similar to the elliptical curve digital signature standard. These are essentially the same. They only differ a little bit from the El-Gamal scheme that we just covered. So the DSA uses two public keys, and the signature and the message are also bundled together. And the difference now is we have two prime numbers that we're going to use, and the second prime number Q is a lot smaller than our original prime P. And this was an evolution of digital signatures, and this protocol was about 5 to 10 times, you know, faster, lighter. It's just an improved version of the El-Gamal. So we're going to start right here, and it's easier to walk through this with an example. So, you know, back to our discrete log problem example, we know that there's a number that exists that's less than P, and when you raise it to any integer, the result is going to be a cyclic group. And you think back from our example in the Diffie-Hellman protocol, that some number that we had was 2, and we raised it to all the integers in the circle of numbers P, and it gave us this cyclic group of all the numbers from 1 to 10. And this second prime here, and this relationship with P, we have a common generator that we share, and this we can overlap these two groups together for some of the math operations that we have to do. And it's the second prime number, this new addition, that made the DSA so much faster, because when DSA was published, this was the number of bits, the space that El-Gamal scheme needed, but the DSA needs much less space. This is what made it 5 to 10 times faster, more efficient, less bandwidth, and so on. So to the public keys, DSA has the same number 1 as El-Gamal, and for number 2, it's slightly different. So instead of the P minus 1, we now have the prime factor of P minus 1, which is Q. And the signature equation is also pretty close. So now we don't have P minus 1, we have Q, and then a little difference in plus or minus. So Alice will give Bob all this information and the message and the plain text, and Bob's going to derive the message, and he has to do this this verification. So That's long. So we'll back this up, and you can take this step by step, and you compute these intermediary values, and they're just combined here. It's just this here is just laying it all out. And again, without going into the math, but it's just like ElGamal. You get down here, as long as the signature is done correctly, this equation on the left that has this equation on the left, V, that has the signature and the message bundled, will equal this equation on the right, R. So V will equal R. Mod Q will equal R mod Q. And for a quick example, so Alice does her calculations, and she passes all this public information to Bob. And again, Bob is using only public information. Alice's 2 private keys are still a secret, protected by the discrete log problem. So Bob checks. And in this case, his R of 20 does equal to the V result he gets of 20. So this is a valid signature. And the last point, back to the speed of the digital signature algorithm, the R and the S, they are incorporated, when it comes to verifying, they're incorporated here in these exponents. And this exponent operation takes proportionately a lot more relatively a lot more computing. So now R and S are smaller since they're a function of the smaller value Q. And they're going to be the same bit size as Q. And this is why RSA, and this is where RSA helps, because it takes this disproportionate computational operation and just makes it a lot easier. So that's why it's 5 to 10 times faster, more efficient, so on. And now on to elliptical curves. And the next step is easy. So elliptical curves, the elliptical curve digital signature standard has all the same components of the DSA, including the second prime number, although now it may or may not be a little smaller. And the equations are the same too. It's just that here we have the elliptical curve equivalent, the analogous of the discrete log problem. X and R have a relationship. They're both in this cyclic group of size A and with the same generator A. And the W, U1, and U2 are the same. And then, again, P is now the elliptical curve equivalent of the discrete log problem. You can see it's all the same variables, and the check is the same. So, and now the public info is also going to include what the actual polynomial equation is for the elliptical curve. And for the math proof, the first 3 steps here of the math proof are going to be the same. And for these last steps, it's just the elliptical curve equivalent. And here's what it looks like. And again, it boils down to if the signature is correct, then the check for V and R, these two will be the same value. And then for a quick example, this is the same equation we used in our last elliptical curve example. You can see the modulus P here, and the number of points in the cyclic group is equal to Q. And recall for elliptical curves that the number of points is roughly equal to P. Could be a little bit less, could be a little bit more. Roughly equal to it. And Alice has her 2 secret numbers and her 2 public numbers, and her 2 public points. And she has R and S. Now, Bob he only needs the public information, and Alice can keep her private keys or private points, or private keys a secret, while at the same time prove that she owns this message. And just a reminder on this verification here, when you're starting at this point 06, you first have to do a point double, and then you go into point addition, which is why the answer ends up being 711. So digital signatures is a way to 100% unequivocally prove ownership of some zeros and ones, of some digital data. And in these schemes, it is only the person that has the right private key that can make the signature. And anyone in the world can verify a signature using publicly available information only.